Howdy everybody, I'm Nipuna Neo Veeratunga, and in this tutorial I'll be explaining the stack register, a brief overview of its use and functionality. Before I begin, I'll be assuming that you have a basic knowledge about the MIPS instructions, mainly add, I, load word, store word, jump and link, and branch not equal. Also, I'll assume you are able to convert C and C++ code into its assembly counterpart. Okay, first we'll have a brief introduction about the stack register. There are 32 integer registers in the MIPS architecture. This is the register naming convention. The registers that are marked in red, which is 0, 1, 26, 27, are generally reserved registers, which means that you cannot change the value in these registers. The register 31 RA is actually a very important register when we are dealing with the stack pointer. The registers A0 to A3 are used to pass arguments into a function. The registers S0 to S7 are used to save values across functions. Registers V0, V1 are used to return values and results. The temporary registers T0 to T7 and T8 and T9 are the ones that are actually available to store temporary values. So what if the callee wants to use more than the allocated amount of registers? For this purpose, you can use the stack register 20, which is register number 29, which grows from the high address to the low address. I'll be explaining this in a minute. To add data into the register or to push data into the stack, we use this instruction. Also, to remove data from the stack, to pop data from the stack, we use this instruction. The stack grows from the high address to the low address. You will better understand this when we move to the example in this tutorial. The stack can be considered as a virtual array where values can be stored and recovered when needed. The part of the stack containing a procedure's saved registers and local variables is its procedure frame. The frame pointer points to the first word of the frame of a procedure, providing a stable base register for the procedure. Frame pointer is initialized using the stack pointer on a call, and stack pointer is restored using frame pointer on a return. What this basically says is this part of the stack contains the procedure's saved registers and local variables. So if the stack starts from here, as I said before, the stack grows from the high address to the low address. So if the stack starts from here, it should be pushing data from top to bottom, and it should be popping data from bottom to top. So when the procedure starts, if the stack pointer is at this position, once the procedure is over, the stack pointer should be returned. It should be restored to this position. You will better understand this when we move to the example. Okay, now for the example. Remember, the one important thing that you should know is that the return address, the value stored in RA, is crucial when executing functions that utilize the stack pointer. After executing a function, the return value may be used in the next part of the program, or it will move on to another function. This is an example of a recursive procedure. In this function, the factorial of a number is computed. This function fact with the argument n. If n is less than 1, it should return 1, else it should return n times the value of function fact n with the argument n minus 1. You can see that this function calls itself. That is why we call it a recursive procedure. This is the translation of that C code into assembly, and I will be going over each of these instructions during this example. So assume A0 equals 2. So that means we need to calculate the factorial of 2. As you can see, I mean, when we are starting this this procedures, the stack pointer is at this position. So what this means is that at the end of this procedure, the stack pointer should be returned, it should be restored to this position. This is a representation of compiling a recursive procedure. You can see, like, the first invocation of fact calls with the argument 4, and it goes to the address stored in this register, which is the caller, which in turn calls fact again with A0 minus 1, which is 3. So this fact should be called until A0 reaches 0, and then it should multiply each of those numbers, which would give the factorial of the number which we need. What this instruction does, it creates room in the stack. Here the value of at this register, at the register RA, is stored in this address. So RA is the address of caller return address is stored in this address, and the value of A0, which is 2, is stored in this address. So the stack pointer is now here. Here it tests whether A0 is less than 1. A0 is 2, so A0 is not less than 1, thus T0 equals 0, and T0 equals 0, so this branch is taken, which is L1. Here L1, the value of A0 is decremented by 1. You can see A0 was 2, here now it's 1, and this jump and link instruction calls the function fact again with the new argument A0 equals 1. Here before the value at RA was the caller return address, but since we are using the jump and link instruction, the new value at RA is the address of the label bk_f. Okay, now A0 equals 1. Here this instruction again creates room in the stack. It now stores the new value of RA in this instruction in this address, which is the address of bk_f. It stores the new value of A0 in this address, which is 1. Again it compares whether A0 is less than 1. A0 is 1, so T0 equals 0. Again this branch is taken, and A0, which is 1, is decremented by 1. Now A0 is 0, 1 minus 1, and again this instruction, which is jump and link, calls the function fact with the new argument A0 equals 0. Again return address, the value at RA is the address of bk_f. Again this instruction creates room in the stack. It stores the new value of RA in this address, which is still the address of bk_f, and it stores the new value of A0 in this address, which is 0. Now A0 is 1, so A0 is less than 1, so T0 equals 1. So T0 does not equal to 0, so this branch is not taken. V0 is 0 plus 1, which is 1. The stack is increased here, and the jump to register instruction goes to the address which is located in this register, which is still bk_f. Here the value at this address is loaded into the register A0. So A0 is 1. The value at this address is loaded into RA. So RA is still the address of bk_f, and again the stack pointer is increased. With the value of B0 is now calculated as A0 times V0. V0 was 1 from before and A0 is now 1, so V0 equals 1 times 1. This jump to register instruction again goes to the address which is located in the RA register, which is the address of BK_F. Okay, again then the value stored in this address is loaded into A0, which is 2. The value stored in this address is loaded into RA, which is the caller return address. The stack pointer is increased. As you remember, when we started the procedure, the stack pointer was at this position. So since now the procedure is ending, we have restored the stack pointer to this point, and V0 is A0 times V0. V0 from before was 1 times 1. Now the new A0 is 2. So the new V0 is 2 times 1 times 1, which is 2. So the factorial of 2 is 2. And this jump to register instruction, this instruction makes the program jump to the address which is located at the register RA, which is the caller return address, which is what we want at the end of the procedure. Okay, in conclusion, the stack acts like a virtual array which stores arguments when registers would not suffice. If the number of available registers is not enough, you can utilize the stack. The stack is an efficient tool when dealing with functions, especially recursive functions, as I explained using the factorial function. Remember, the value stored in array is crucial when dealing with the stack. This is perhaps the most important point you should take out of this tutorial. Not all programs need the use of the stack pointer. If the available amount of registers is enough for the program, you may not need to use the stack pointer. That concludes the tutorial. Thanks and gig 'em.